Hello everyone and welcome to Unit 2 of the ROS Navigation course, where we will talk about mapping. So, if you have completed the basic concepts chapter, you should know at this point that in order to perform navigation, it is very important to have a map. In fact, it is the first thing we need. We need to have a map of the environment we want to navigate. Yes? Then in this unit we are going to see how you can create a map from zero. Yes? Before starting, I want to introduce you, if you don't know it yet, to RViz, because RViz is a very important tool in the whole navigation process, because it allows you to visualize many things. For instance, in this case, it allows you to visualize the mapping process, how the map is being built, and how the map looks, and what are the readings from the lasers, for instance, many things. So RViz is a very important tool in navigation. So in mapping, specifically in mapping, we will basically use two tools of RViz, which is the laser scan display, which will allow us to visualize the laser readings, and the map display, which will allow us to visualize the map. So yes, let's do this first exercise, this first guided exercise. So first of all, we are going to launch our mapping node using this command here. Yes, ROS launch startable navigation in gazebo gmapping demo.launch. So we are going to execute this command here. We are going to execute in another web shell RViz. So we are going to launch RViz, and by hitting here in the graphical interface button, we will be able to visualize the RViz window. There we have it. Excellent. So visualize laser scan. So in order to visualize, I'm going to remove all of this, and I'm going to start from zero. Okay, so in order to visualize the readings of the laser, what you have to do is to come here to the add button, and then in the list of elements there is one that is called laser scan. So you can add this, and then you will have to introduce the topic where the laser data is being published. In this case, for this simulation, the laser data is being published in the Kabuki laser scan topic. Yes? So I'm going to introduce here the name of this topic. Here we have it, Kabuki laser scan. There we are. Now the lines are very tiny, so I'm going to make them a little bit bigger. Let's put this to 0.5. There we are. So here we can visualize what the laser is detecting. Yes, these are the readings from the laser mounted on the Kabuki robot. It is up here. Yeah, this is the laser. So these red lines I see in RViz are the readings from the laser. Okay, so now I'm able to visualize the laser. But for the mapping process, of course, I would like to visualize the map. So for that, it's very simple as well. You have to come again to the add button and select the where it is. Map, here it is, the map option. Okay, so I will add this map option. Then in the topic, I will need to state the topic where the map is published, which is map. Here we have it. Okay, then by adding this display, I can visualize the map. This is the map that is right now Yes, because I haven't started to move the robot in order to build the wall map, yes? But this way I will be able to visualize how the map is being created during the mapping process. Yes? So these are the two main displays you need to take into account when working in the mapping process. All right? Excellent. So yeah, there we are. Okay, yes, if you want, you can save your configuration, which will load it right as it is right now. You can do it by coming here, save configuration, for instance, save configuration as, if you want to save with a special name, whatever, okay? But yeah, that's up to you, okay? It is done like this, very easy. So let's keep moving and let's start to build the map itself. So for that we'll need to move the robot, of course. So we will launch the keyboard teleop program in order to control the Kabuki robot through the keyboard. So let's launch the keyboard teleop. There we are. And now what I want you to do is to start moving the robot all around the environment using the keyboard until you have a full map of the environment, okay? So I will leave you some time to do it. It's done quick, I think. And meanwhile, I will be doing it myself, and I will see you when I have finished it. So see you in a moment. Great, so I am done. As you can see here in RViz, I have created the map. It has still some small errors, but it doesn't matter because it is just an example. So I hope you also have created your map. It should look something like this. Like this. Yes, this is how your map should look. Okay. And yeah, that's it. So now, once we have done this, let's explain a little bit what's going on here. Okay. So basically what we are doing is to perform SLAM, which means simultaneous localization and mapping. Okay, so SLAM is the name that refers to building a map of an unknown environment while simultaneously localizing the robot in the map that is being built. Okay. This is a problem in robotics, which is called SLAM, and which is solved in ROS by using the gmapping package. Okay, so what we are doing here during the mapping process is SLAM. Yeah, it's known as SLAM, which means simultaneous localization and mapping. Okay, this is a robotics problem that we are solving in ROS by using the gmapping package. And this gmapping package basically what does is to implement an SLAM algorithm called gmapping. Okay, this is an algorithm that solves this SLAM problem, and this is the algorithm that ROS uses in order to create a map of the environment. Yes, in the mapping process. So we don't need to worry about this because we already have it available in ROS. We just have to worry about configuring this package depending on the needs we have, on the robot we use, on whatever. Okay, but this is already solved. Okay, by ROS using the gmapping algorithm. So we don't have to worry about this. Okay. So the gmapping package contains a ROS node which is called SLAM gmapping. Okay, and this node allows us to create a 2D map. Yes, this is a 2 dimensions map. So this SLAM gmapping node allows us to create a 2D map by using the data from the laser and from the position of the robot. Okay, so this node basically reads data from the laser and the transforms of the robot and turns this data into a OGM, an occupancy grid map. Okay? We are going to see later what is a occupancy grid map. Yes? So basically, what happened while you were creating the map in that process was, first, you have used a previously created configuration launch file. Yes? So you launch it, first of all, you launched this command here. Let me look for it. Okay, never mind. Let's get it from here again so you can see it. Okay, there we are. Let's go back here. Okay, so the first thing you did was to launch this command, yes? And what this does, what this launch file, the gmapping demo.launch file, what does is to launch a SLAM gmapping node, which it is already configured. In this case, we have already configured it to you, so you don't have to do it, okay? You will learn how to do it later in the unit, don't worry, okay? But in this case, you launched an SLAM gmapping node which was already configured, okay? So that's why what you were doing with this command. Yes? Then, the SLAM gmapping node that you started with this launch file subscribes to the laser data, yes, which are these red lines you are seeing here. Yes, this is the data that is being captured by the laser. Yes, so this SLAM gmapping node subscribes to this data and to the transform data. Okay, and with that data, knowing that data, it is able to build this map you see here. Okay, so it gets as an input, this SLAM gmapping node gets as an input the laser and the transforms data, and with that data it builds the map. Okay, then this map is published into a topic which name is map. Yes, so this map is published into a map topic. That's why you are able to visualize this map through RViz. Yes, because this data at the end is information that is being published into a topic. Okay, so this is basically the process that's happening after all you have done while creating the map. Yes, then yeah, as I said, this map is an OGM, an occupancy grid map. So this occupancy is represented as an integer. Yes? So when the integer is 0, it means that that area is completely free. Okay, so there's no obstacle there. When the integer is 100, means that that area has an obstacle. Yes? So a 0 will be printed here as this gray color. Yes? And a value of 100 is printed here in black color, as you can see. Yeah? This black color means that there are obstacles there, that the laser is detecting something there. Yes? And finally, we also have a -1 value, which means completely unknown. Yeah? Okay. So now, once you have created the map, once you have your map created, what can you do with that map? Well, the first thing you can do, of course, is to save the map. Okay? in order to have it, of course. Then the command in order to save the map is this one here, ROS run map server map saver -f and the name you want to give to your map. Yes, so let's here you have a very simple exercise in order to do this. So let's try it. Okay, so let's see. Yeah, here I have the launch file with the gmapping node, RViz. Okay, so I'm going to stop here the keyboard teleop. I don't need it anymore. So let's go to our workspace, and here I can execute this command. So ROS run map server, which is the package, map saver, which is the node, -f, and I'm going to call it my map. Okay, so let's execute this command. Okay, everything went fine, and now, as you can see here, it appeared two new files, mymap.pgm and mymap.yalm. Okay, so what are these? Well, these are the files that are defining my map. Yes, the yalm file, it is a regular YAML file, so you can read it and understand it easily. Yes, it contains information about the map. For instance, the image of the map, in which file it is the image of the map. In this case, it is in mymap.pgm. Yes, the resolution of the map, the origin, which is the lower left pixel of the map, the thresholds for occupied and for free. Yes, it contains information. You can check it here. It contains information about this map. And the PGM file, it is an image of your map. Yes? And PGM, this extension is the format, which is a portable gray map. This is a quite a special extension, and not all the programs can read it, yes? But for instance, I'm going to download this mymap.pgm file. There we are. And I'm going to open it using GIMP in this case. Okay, so here I have my image, yeah, the image of my map. Okay, so let's, yeah, so I'm gonna close this. This is exactly the image of the map I have created here. Yes? Okay, so let's close this. Image. Excellent. Okay, so when you save the map using this command, what you will do is to create two files. A YAML file that contains some metadata information about the map, and a file containing an image of your map. Okay? Excellent. So let's keep moving. Alright, so what else can you do with the map? Yes, you can provide the map. Once you have your map saved like this, you can provide it for other nodes to use it. Yes, for instance, for localization or for path planning, you will need a map. Yes, then once you have your map saved like this, you can provide it. You will see examples in future units of this, okay? But yes, you can provide the map to other nodes, okay? So you can call this service, static map service, in order to get a map. Yes? And how a map is provided, how a map is published, let's say. Well, it's published by using two topics: the map metadata topic and the map topic. Yes, the map metadata topic will contain the metadata of the map. Yes? And the map topic contains the occupancy data of the map. Yes? So let's see an example of this in this exercise here. So the command in order to launch the map server node, in order to provide a map, is this one: ROS run map server, and the name of the YAML file of your map. Yes? So let's do a quick exercise here in order to test this. So yeah, let me stop everything. Okay, so now I'm going to execute this command here, which is ROS run map server my map.yalm. Okay, well, in this case I will go to my workspace. There we are. ROS run map server my map.yalm. Okay, so I'm going to execute this command. There we are. So here you can see the feedback: loading map from image mymap.pgm. Yes, this pgm file we have here that we saw previously, that was the image of our map. Yes, so now with this command what we are doing is to read this map and provide it so anyone can access it. Okay, so as I've explained it here, this is done through two topics: the map metadata and the map topic. Yeah, so now I can have a look at these topics. For instance, I can do a ROS topic echo of the map metadata topic. Okay, here we have it. So here I have some metadata of the map I am loading, from resolution, width, height, the origin, lower left pixel of the map. Yes, so here I have the metadata information of the map. Then also I can do an echo of the map topic, which it is quite more complex, the message. And as you can see, this is composed of the occupancy grid we told before. Yes, this is a huge amount of data, so it is impossible to see. But here, basically, you will find -1 value, which if you remember, means a completely unknown space. Yes, let's go back here. There we are. Yes, so if you remember, a -1 means completely unknown. A 0 means completely free space. And 100 means completely occupied. Okay, so this is the data that is being published in the map topic. Okay, so we have the map topic that contains the occupancy data of the map, and we have the map metadata topic that contains the metadata information of the map. Okay, excellent. So let's continue with our unit. Okay, so now here you have an exercise that I recommend you to do, which is to create a launch file that launches the map server node. So now I am launching this map server node using this command, okay? But now I want you to do it by using a launch file. Okay? So as always, you can pause the video here if you want in order to do the exercise, and then when you have finished it, unpause the video and continue with the lesson, okay? I will continue non-stop explaining the different things in the unit and presenting the different exercise, okay? So yeah, let's continue. Okay, so right now we have seen these two topics where the map server node publishes, yes, the information of the map, the different data of the map, okay? It publishes it in the map metadata and the map topic, okay? But also, as I've said before, this node provides the static map service, which allows us to also get the data by calling to this service. Yeah, so we're going to try this right now with this very simple exercise as well. So we are going to do a call to this static ROS service call static map service, which uses an empty message, as you can see here. Yeah, so by calling to this service, I can also get the data from the map. Yes, as you can see here, this is a huge message as always. Yes, but at the end, what I will get by calling this service is the information from the metadata and from the occupancy data. Yes, so by calling this service, I get both the data from the map metadata topic and the data from the map topic. Okay, so this is an alternate way to get a map. All right, so now here you have another exercise, which is to create a service client that calls to this service. Yeah, so now I have done it with the ROS service call command, but now for this exercise you should do it by creating a service client. Okay, excellent. So let's continue. And now that we have seen a little bit more about maps, that you have learned some things, let me say two things. Okay, let me point out two important things. The map that you have created, yes, the map that you created here, the map that you created at the beginning of the unit is a static map, so it doesn't change. It will always be like this, okay? So if the environment changes in some way, you will need to create a new map, okay? This is very important. The map you create is an static map. It doesn't change, okay? And another important thing is that this map is a 2D map. So the obstacles that appear in the map don't have height information. Yes, so for instance, if you try to use a map like this one, a 2D map, to perform drone navigation, it won't be valid. Yes, there are other packages in ROS that allow you to generate 3D maps. Yes, in fact, for instance, in the Robotics Academy, you have a course to check the AirTap map package, which is a 3D mapping package. Yes, but this map you have created, the maps that we are working to work with in this course, are 2D maps. Yes, so this is very important also for you to know. All right, excellent. So let's keep going. So the next thing I want to mention are a couple of hardware requirements. Yes, so in order to build a proper map, you basically need to fulfill two requirements. One is to provide good laser data, and the other one is to provide good odometry data. Okay? Here you have a small exercise in order to check how this data is provided, in this case, through which channels, topics it is provided. But yeah, you need to have this in mind. So you need to provide a good laser data and a good odometry data in order to be able to build a proper map. Okay? Excellent. So yeah, let's have a quick look now at transforms. Okay, I talked a little bit about this in the previous unit, about the importance of transform. Yeah, but let's have a deeper look. Yes, to this issue. So, okay, in order to be able to use the laser, we need to tell to the system where this laser is placed in the robot, referenced to a point of the robot. Yes, this point usually is the base link point. Yes, so this means that we need to set a transform between the laser and the robot. Okay, yeah, we are going to see this better here. But basically what we need to tell to the system is where the laser is placed in the robot. Yes? And this information is called transform in ROS. And it is published in a transform tree. Okay? So let's clarify a little bit of this. A little bit all of this. So in order to be able to use the laser data, we need to tell the robot where, position and orientation, the laser is mounted in the robot. Yes? This is what is called a transform between frames. So basically a transform specifies how data expressed in a frame can be transformed into a different frame. Yeah? So, for example, let's come again to the simulation. If a laser detects an object, yes, we need to know where this object is, not based on the laser, but based on the robot, because this is the important information. How far away is this object from the robot? In which direction is of the robot? It is in front of the robot? Is it back of the robot? It is at the right side of the robot? Yes. So we need to reference this obstacle to the robot. Yes? Are you understanding? So, yeah, let's read here the example. So, if you detect an obstacle with the laser at 3 centimeters in the front, this means that it is 3 centimeters from the laser. But that doesn't mean that it is 3 centimeters in front of the robot. Yeah? That depends on how or where the laser is placed in the robot. Yes? So to know the distance from the center of the robot, we need to transform this 3 centimeters reading from the laser frame to the base link frame. Yes? So we really, for navigation, we don't care how long is an obstacle from the laser. We need to know how long it's an obstacle from the robot. Okay? And in which direction, of course. So that information is contained in a transform. Okay? So, as you can see in the scheme here I have created, in this case, this block here, this yellow block, will represent the base link of the robot. Yes? And this orange block will represent the laser. Yes? So it's not the same if the laser is mounted here, how it is in this picture, or if it is mounted here in the left side, or if it is mounted in the center. Yes? This makes a lot of difference. Okay? So this needs to be specified in the transforms of the robot. Okay? For the case of our robot, as you can see, here we have the base link, which is placed in the base of the robot, and here we have the laser sensor link, yes, which is placed in the base of the laser. Yes, so this relationship between these two links, it is the transform. Yes? So, summarizing, okay? Summarizing. We need to define this relationship in terms of position and orientation between the base laser link, between the laser link, yes, and the base link. So if we know that the laser is at a distance of 20 centimeters in the y-axis and 10 centimeters in the x-axis, we need to tell this to the robot. We need to tell, hey, robot. So this is like talking directly to the Kabuki robot. Hey, robot, I want you to know that you have, from your base link 20 centimeters up, you have a laser, okay? So this, yes? So it is like telling the robot this information. Hey, you have a laser mounted 10 centimeters up in your y-axis, for instance, okay? So this relationship between the position of the laser and the position of the base of the robot, it is known as the transform between the laser and the robot. And this information is very important when creating a map. And in general, for anything, this is very important. Transforms are very important. Okay? And yes, I know this is a lot of new information, and this is not the course to talk about transforms, but I just wanted to introduce a little bit this idea. Yeah, but if you want, for instance, in the Robot Ignite Academy, we have a course dedicated to transforms. Yes, so you can get deeper into this issue, this topic, which is very, very interesting. Yes, here I just want to explain this importance when creating a map. Okay, so for the SLAM gmapping node to work properly, we will need to provide two transforms. Yes? We will need to provide the transform from the laser to the base link, to the base of the robot. So we will need to provide the transform from the laser to the robot, and as well from the robot, from the base link of the robot to ODOM. Yes, this transform is usually provided by the odometry system. Yes? But these two transforms, we need to provide them if we want that the SLAM gmapping node works properly. Okay? Then, these transforms, since the robot needs to access this information at every moment, these transforms are published into what is known as a transform tree. Yes? The transform tree is basically like a database where you can access information about the different transforms. Yes? And with this command, you can have a look at this transform tree. Yeah? So let's do very quickly this example. Okay, I'm going to execute here this ROS run TF view frames. Okay, so this will generate now here, you will see a PDF file containing the data of this transform tree. Yes? So let's wait, here we have it. Okay, so again, you can download if you want this file and open it. And here you can access the transform tree of this robot. Yes? As you can see, there are a lot of transforms. Yes? So here, for instance, we can see the base link, which is connected to the ODOM as well. And this should be connected also to the laser link, which it is, I don't remember, let's see if we find it, but it should be somewhere around here. Here it is. Okay, so here we have the laser. Yes. So as you can see, everything is connected. The laser is connected to the base link, and the base link is connected to the odom frames. Okay. Well, never mind. Let's close this. We don't. Let's code all of this. So yeah, I hope you have understand a little bit what I have tried to explain here and the importance of transforms. Yes, in the world navigation process, but in mapping specifically, it is very important in order to create a good map. Okay, so now here, here we have some more information about how to publish a static transform. But well, I will skip this part because actually this is not directly related to mapping itself. Yes, this is more a concept of transforms. So if you want to know more information about transforms, you can go to the TF 101 course that we provide in the Robotics Academy. Okay, so for now, I'm going to skip this section here. I'm going to skip this, and I'm going to go directly to create a launch file for the SLAM gmapping node. So until now, you have been using a launch file which launched an already configured SLAM gmapping node. Yes, it was this command you did at the beginning of the unit. Yes, so here you are using an already configured SLAM gmapping node. Yes, you are launching an already configured SLAM gmapping node. Okay, so now we are going to see how you can create yourself your launch file for starting an SLAM gmapping node. So let's make this bigger. Okay, so for creating a launch file, all you will need to do is to configure to set some parameters. Yeah, it's very simple, as you will see. Okay, but it has quite a lot of parameters, so you will have to set them properly in order to make your SLAM gmapping node work properly, of course. Yes, there are, you can have a look if you want at the full list of parameters here in this link in the ROS wiki, but we are having to have a look at the most important ones. Yeah, so I'm going to divide these parameters in some groups. So the first one is the general parameters. In the general parameters, we will specify the base frame, the map frame, the odom frame, and a map update interval. Yes? So the base frame is the name of the frame attached to the mobile base. Usually this is base link, and the default value of this is base link. Yes? Then you have to indicate as well the frame attached to the map, which usually also is map, and the odom frame, which usually is odom. Yes? Finally, you have here another parameter, which is the map update interval, which sets the time in seconds to wait for updating the map. Yes, so these are 4 general parameters that you need to take into account. Okay, so now what you will have to do is to do this exercise 2.1, yeah, which is to configure yourself your launch file. So for that, there are a couple of steps. Okay, I think I'm going to do this one with you, and the other ones I will leave them for you to make them alone. So, okay, in this case, what you will need to do is, from the touchable navigation package, you will need to find this gmapping demo launch file, which is the file that you have been using, that you used it at the beginning of the unit. Yes, so let's go for find this file in the Turtlebot navigation gazebo. Here in the launch directory, you can see this gmapping demo.launch file. Yes? So if we have a look at this gmapping demo launch file, we can see that what it is really doing is to call another launch file, which is in the Turtlebot navigation package, yes? So this launch file is calling to this gmapping launch XML file, yes? This is what it is really doing, yes? So, yeah, okay. So the next step will be to create a new package, name it my mapping launcher. Okay, so let's do this. Okay, so let's do this. Let's see. Okay, well, let's create a new package which will be called my mapping launcher. There we are. Yeah, I'm going to remove all of this, at least the frames, not the map. Okay. So inside this package, create a directory, name it launch. Okay, so I will create a directory named launch. And inside this directory, create a file named my gmapping launch.launch. Okay, new file, my gmapping launch.launch. There we are. Excellent. So then inside this file, copy the contents of the gmapping launch XML file. Okay, so oops, sorry. Clear, ROS CD, Turtlebot. So if you remember, when we checked this gmapping demo launch file, which is here, we saw that this is actually calling another file, which is this gmapping launch XML. Yes, this gmapping launch XML. So this file is contained in the Turtlebot navigation package within the launch includes gmapping directory. Okay, so let's go to this ROS CD Turtlebot navigation package. And here it was in launch. Yeah, launch includes. Okay, yes, includes gmapping. Okay, yeah, so here we have it, the gmapping launch XML file. Okay, so what I'm going to do is to copy this launch file to my workspace, okay? User, Capking workspace, SRC. So I'm going to copy it here, and now I will copy the whole content of this file to my launch file, okay? Let's do this bigger. There we are. So now I have the contents of the gmapping launch XML file into the launch file I have just created now. Yeah? Excellent. So let me delete this. Okay. Then modify the launch file you just created and set the map update interval parameter to 15. Okay. Launch the gmapping node using the new launch file created and launch RViz with your previously saved configuration. Excellent. Now, move the router around and calculate the time that takes to update the map now. Okay, so basically now, as you can see, here you have all the parameters that you can set up for the SLAM gmapping node. Yes, so now, for instance, you have here the base frame, odom frame, yeah? You have them here. Okay, so basically now you can access to all the parameters, you can modify all the parameters that will configure the SLAM gmapping node, yes? So in this case, it asks you to modify one of them and test it, okay? I will leave this to you, yeah? But the important thing is that you get to this point where you have your launch file, like this, and you can modify the values as you want, okay? Excellent. Then, okay, let's have a look at the laser parameters. Here, we are going to have a look at the max range, max U range, and minimum score. So the max range value, which is, you can see it here, for instance, the max range, yes? The max range parameter sets the maximum range of the laser, okay? So beyond this value, the laser doesn't detect anything. Yeah, the laser beams don't arrive that far. Let's say it like this. Okay, so this value should be set to something slightly higher than the real sensor maximum range. Okay, so if you buy a laser, in the information in the datasheet, you will see that that laser has a maximum range. Okay, so when you configure your gmapping, your SLAM gmapping node, you should set this max range value to something slightly higher than that real maximum range. Okay, then we have this max U range, which means max usable range. Yes, this max U range parameter sets the maximum usable range of the laser. Okay, so your laser can have a range of 30 meters, yes, but if you set this max U range to 10, in your simulation, when you create your map in your simulation, that laser will have a range of 10. Okay, so yeah, the laser beams, despite the real value, are cropped to this value. Okay, then finally you have as well the minimum score parameter, which sets the minimum score to consider a laser reading good. Okay, excellent. So here as well you have another exercise to modify and test some parameters. I will leave this up to you. Okay, and then we have here the initial map dimensions and resolutions. Yes, these are other parameters in order to define the initial map size. Okay, initial map size in X, Y, minimum maximums, and delta, which sets the resolution of the map. Okay, this is some metadata information of the map. Yes, this is in order to configure the size, the initial size of the map, and the resolution of the map. Okay, then finally, you have exercises here that you should do. I will skip them, yes, because I'm just explaining a little bit the different parts. So finally you have other parameters, and in this section we can find the linear update, which this parameter sets the linear distance that the robot has to move in order to process a laser reading. Yes, so you can define, for instance, that each time the robot moves 10 centimeters in the linear direction, of course, you will process a new laser reading. Yes, you can configure this with this parameter, and the same for the angular update. So each time the robot rotates a certain degrees, you will process a new laser reading. Yes? Then you can also configure this using the temporal update. Yes? So this doesn't depend in the angular movement or the linear movement of the robot, but it depends on the time. So sets the time in seconds to wait between laser readings. Yeah, so each 2 seconds process a new laser reading, for instance. Okay, this is usually the default value is -1. So if this value is set to -1, this function is turned off. Okay. Then finally we have this particles parameter, which sets the number of particles in the filter. This is for localization purposes. Okay. Don't worry, you will better understand this particles thing in the next unit, in the localization unit, okay? Okay, yeah. So now you have, when you finish all this exercise, you will see how to modify the parameters directly in the launch file. Yes, modifying them directly in the launch file, okay? But there is another practice which is much more cleaner. Yes, which is to load a parameter file, a YAML file with these parameters. Yes, And this is done using this ROS param file. You put the YAML file where you have your parameters and you load them. Okay, this is an alternate way to do it, so you should try this exercise 2.5 as well. Yes, so at the end what you will have to do is to create this parameters file containing all of these parameters. Yes, then you will remove these parameters from the launch file and you will just insert a line like this one, loading your parameters file. Okay, so this is what I want you to do in this exercise 2.5. Alright? Well, here you have the solution. You shouldn't look at this, okay? But as you can see, at the end you will have a launch file which is much more cleaner and a parameter file where you will define all the parameters. Okay? Then finally, you have a couple of sections more in this unit, but these ones I will let that you make them by your own. Yes, because these are, let's say, they are not mandatory sections. Okay, but this is extra knowledge and very interesting knowledge that you can get from related to the mapping process. Yes, so for instance, one is manually modifying the map. So since you have the map as an image, you can modify this map by adding, let's say, imaginary walls. Yes, so when this map is processed into ROS, these black lines are considered places where the robot cannot go through. Yes, so you can, for instance, manually modify this image using Paint, for instance, or whatever tool you want to use, and add a black line. Let's say, in this case, it's here. You can see, yeah? So we have added a black line here. So now, the robot in the simulation won't be able to pass through this line, despite in the simulation there's nothing there. Yes? So if you go here to the simulation, you can see that there is nothing here. There is no wall here. Yes? So the robot could perfectly go through this zone. Yes? But if you modify your map like this, then you will ban your robot to go through this zone. Yes? Because it will think that there is an obstacle right there. Okay? And then finally you have also this last section, which is to build a map using logged data, using a back file. Okay? So yeah, you can do this if you want, but I will let you, everything is very guided, yeah, so you have step by step what you need to do in order to complete these sections. Okay, so I will let them to you. You can do it by your own. And yeah, I will finish here this unit, and I will see you in the next unit where we will talk about localization. Okay, so see you there. Goodbye.